Hello, future doctor. My name is Alex. Welcome to this high-yield science lesson on Hess's Law. I'm actually really excited about this upcoming one because Hess's Law might be something that's challenging to relate to real life, or even just to something that's relevant to you as a hopeful physician. But actually, it has great relevance, not only something that you do every single day, but increasingly so in medicine. So with that mysterious introduction in mind, let's dig right into our learning goals for today. After this lesson, you'll be able to calculate a compound's standard heat of combustion using Hess's law, and ultimately you'll be able to use that in order to explain the nutritional properties of carbohydrates, lipids, and proteins. Take 1 minute to read this question stem. In the first part of the question stem, essentially everything that's coming before the heat of formation table, the focus is on the bomb calorimeter, how it works, and everything else. But that's not information we're actually going to need because we're simply asked to contrast the heat released by 10 grams of glucose versus 10 grams of xylose. So likely the only thing we're going to need is everything from the table, including the table, down. You can take a moment for yourself to decide how you think those heat values are going to compare. It's fun to have a prediction going into this lesson. The first thing we have to do here is to figure out our balanced equation for the combustion of our sugars. That's really important. Anytime you have a reaction happening and you're going to have to calculate some values, make sure you're dealing with the correct coefficients. So in any case, this particular prompt is telling us how can we write an equation for all carbohydrates? That means we have to find a molecular formula that's going to hold true for all carbohydrates. What would that empirical formula be? The three atoms that make up a carbohydrate are carbon, hydrogen, and oxygen. You always have in any carbohydrate twice the amount of hydrogens and carbons and some amount of oxygen. That being said, on the MCAT, the carbohydrates you see will pretty much have a 1 to 2 to 1 ratio for these three atoms, so we can summarize every carbohydrate in such a way. Next step, equilibrate. Where do we look first to equilibrate? Carbon dioxide is a good place to start since it's our only source of carbon on the product side. And carbon dioxide would be released for every oxidized molecule of carbohydrate. Next, water, since it's our only source of hydrogen on the product side. The coefficient here is still N. And finally, what's the coefficient for oxygen on the reactant side? Still looking at N. So it's nice now because we look at xylose and glucose and we see that they follow the 1 to 2 to 1 ratio. So we can use the standard combustion equation above to quickly equilibrate our reactions for xylose and glucose. For xylose, N equals 5, and for glucose, N is equal to 6. Now we look at these combustion reactions, and it's pretty obvious that we're dealing with the exact same products and reactants, except for one compound. That compound is the sugar itself. So it's worth exploring how the heats of formation of xylose and glucose compare. That way we have this information handy for upcoming calculation questions. Looking at the table in the question stem, xylose's heat of formation is minus 1057.8 kilojoules per mole, while glucose's is minus 1274.5 kilojoules per mole. What fraction can we approximate this ratio to? 10/12 is a perfect estimation here, which of course is equivalent to 5/6. With this prompt, we're getting closer to answering which sugar will give off more heat during combustion. But it's interesting because we're asked to calculate glucose's heat of combustion using Hess's law, but the setup is already there for us. Note that Hess's law is really highlighted in the first line of calculations. You can calculate the enthalpy of a reaction simply by adding the heats of formation of the products and subtracting to that the sum of the heats of formation of the reactants. The only thing that's missing here is the heat of formation of oxygen, which is not given to us in the table of the question stem. What's the heat of formation of oxygen? Because the heat of formation is a change of enthalpy during the formation of a compound from its constituent elements in their standard states, and oxygen is in its standard state, the standard heat of formation must be 0. In other words, if you give me O2 gas, I won't need any energy to turn it into what it already is. Because that missing value is 0, the heat of combustion of glucose is minus 2537.3 kilojoules per mole. We just looked at glucose, and now we necessarily have to shift our attention to xylose. This prompt is asking us for the short way to find xylose's standard heat of combustion. Let's contrast that first with the long way. What would that be? What would the long way to find xylose's standard heat of combustion be? Just repeat everything we've done with glucose, right? Set up Hess's law, gather all the heats of formation, etc. But that's very long. Instead, what line of calculation from the previous question prompt might be useful for xylose? the line where we have all the coefficients appear, because everywhere we had 6's for glucose, we have 5's for xylose. So we can take that line and basically copy paste it for xylose while changing glucose for xylose and all the 6's for 5's. Now the last thing is, we previously determined how the heats of formation of xylose and glucose compare. That of xylose is 5/6 that of glucose. Putting 2 and 2 together, how can we convert the heat of combustion of glucose to that of xylose? We can simply multiply it by 5/6. Doing that, we find that the standard heat of combustion of xylose is minus 2114.4 kilojoules per mole. Now remember from the question stem, we're dealing with 10 grams of each sugar, which means we'll have to use molar masses. We don't need to calculate the exact values because we're just interested in how the heat released will compare. What is the ratio of the molar mass of xylose to that of glucose? Again, it's going to equal 5/6 because we see here that xylose contains 5/6 of all the atoms that glucose contains. Let's bring this all together. This question prompt is asking us to answer the original question, which is to say, how will the heat released by 10 grams of each sugar compare? Again, this is a comparative analysis, so we're not actually interested in calculating any exact value, which is why we set out our heats of combustion with the ratio we found earlier. Standard heats of combustion implies 1 mole of reactants. What do we need to multiply it by to get the heat released by 1 gram instead? Well, the unit for the heat of combustion is joules, and we want joules per gram, so we can multiply by the inverse of molar mass. Again, we're working with the ratios here, not the actual molar mass. Then the final step is to multiply by 10, since we're looking at 10 grams of each sugar, and then we can duplicate the same thing for xylose. Time to simplify. We can cancel out the 6's on glucose's end, the 5's on xylose's end, the 1 mole's pretty much on both ends, as well as the 10 grams. Looking at this, how did we find the heat released by the two sugars compare? 10 grams of each sugar release the same energy. Mind-blowing, isn't it? Okay, this might not be totally obvious from this line of math, so let's try to visually conceptualize it. Let's look at our two sugars here. In purple, we have a certain amount of glucose, and in green, the same amount of xylose. If we overlay them, we see that xylose has 5/6 the molar mass of glucose, and we remember that every molecule of xylose releases 5/6 the heat that glucose does upon combustion. Now here we're showing the mass difference visually, so it looks like we're talking about volume, but the idea is the same. We're dealing with 10 grams of each sugar, so let's see what 10 grams of these sugars look like. We see that we can fit 1, 2, 3, 4, 5 of these glucose blocks in 10 grams. But if we look at xylose, we can fit 1, 2, 3, 4, 5, 6 of these blocks in 10 grams. So the idea is, in 10 grams, you can fit 6/5 more molecules of xylose than glucose, but each molecule of xylose releases 5/6 the heat that glucose does. And so we've seen mathematically and visually that 10 grams of each sugar releases the same amount of heat. And this explains why each carbohydrate releases 4 calories per gram, and each lipid 9 calories per gram, and each protein 4 calories per gram. Then there's alcohol at 7 calories per gram. In the end, the idea is always the same. The bigger the molecule, the more heat it releases, so the greater its standard heat of combustion, but the less of it you can fit in 1 gram. You can relate this to the age-old question: what weighs more, a ton of bricks or a ton of feathers? They both weigh the same, but you have many more feathers in a ton than you have bricks. In fact, if you had recognized from the get-go that glucose and xylose were both sugars, you could have realized right there and then that both would release 40 calories. Talk about saving yourself some really tough math here. Let's review what we've done here. First off, we went over how to calculate a compound standard heat of combustion using Hess's law, and we've seen how that helps us explain the nutritional properties of the macromolecules, so carbohydrates, lipids, and proteins. I really hope this lesson encourages you to relate challenging concepts to real-life applications. Not only will you know your content better for doing so, but you'll know it for a longer time, and having different ways to think about the same thing is always uber useful on the MCAT. Keep up the stellar work.